Okay, let's get back into these related rates questions. I know, it's kind of tricky. It's only going to get easier by putting in work. So you got to practice, and then the more you practice, the easier it will get. It's not easy, and it won't ever get super easy, but it will get easier, right? The more you practice, the more exposure you get to it, the better you'll get. Okay, let's do a second one. A spherical balloon is being inflated at a rate of 10 pi feet cubed per second. At what rate is the radius increasing? Let's think about drawing a picture. Spherical balloon. Right, of course, the spherical balloon is basically only defined by the radius, and it says that spherical balloon is getting inflated, so that balloon should be getting bigger, and it says it's increasing at a rate of 10 pi cubic feet per second. So notice that's your dv dt. It gives you the units for volume over units for time. So there's your dv dt. And then it says at what rate is the radius increasing? So it wants you to answer what is your dr dt. We know the dv dt is 10 pi. Is positive because as that balloon is getting inflated, it's increasing. And then at this one moment that we're going to investigate, the radius is 2. Okay, so again, if it starts me with the dv dt, we're going to need to begin with the volume equation. And the volume of a sphere, if you flip back to the previous page, you'll see it. But the volume of a sphere, you really should know this, is 4/3 pi r cubed. Okay, so there's your volume. Think about it. It's got v's and it's got r's. So if I took the derivative, it's going to have a dv dt and it's going to have a dr dt. But it's okay to have a dr dt because that's what we're going to solve for. You wouldn't be able to solve for it if it's not even there. That wouldn't make sense. So it's okay to have r's in my original because that means you're going to have r primes or dr dt's in the derivative. That's good because that's what we want to look for at the end. And it's also okay to have v's in the original because that means you're going to have dv dt's in the derivative, or v primes, but I know what the v prime is. Right, so those are both good, right? I don't have extra variables in this question. Here it's just straight up start with the volume, take the derivative, plug in what you know, solve for the one thing that you don't know. So let's do it. Here I'm going to take the derivative with respect to time. I'm going to do the prime notation just to show you that you could do it either way. V prime, or dv dt if you like. This 3 multiplies to the front. It's going to cancel with the 1 down there, so I have 4 pi r squared. Don't forget your chain rule since this is r's and you're doing the derivative of t's, times r prime. Right? So we had v prime equals 4 pi r squared r prime. I've taken the calculus. That's my one calculus step. You've taken the derivative. So now it's plugging everything. The dv dt was 10 pi. Then we have the 4 pi. Now I can plug in the radius. The radius was 2, so 2 squared would be 4. And then the dr dt is what we're looking for. Okay, so that's all 16 pi divided over 10 pi divided by 16 pi. That's your r prime. The pi's are going to cancel. 10 over 16 reduces to 5/8. And then let's put units on this. I need, right, that's dr dt. So you need the units for the radius over the units for the time. The radius looks like it's going to be in feet. And then your time is in seconds. And again, let's think, does it make sense to be positive? Or should it have been, or should it have been negative? Well, think, if that balloon is getting inflated, the radius, just like the volume, should be increasing. So yes, the derivative should be positive. Always just check the positive and negative at the end because it's easy to get them switched and get them backwards. Okay, so that one's not too bad. It just is pretty simple. Start with the volume, take the derivative, plug in what you know, solve for the one thing that you don't know. Let's do the next one. This is a pretty typical Calculus 1 question. There's always ladders falling down in calculus. I don't know why. These mathematicians just can't put up their ladders correctly. That's okay. A ladder, which is 25 feet, is leaning up against a wall. If the foot of the ladder is being pulled away from the bottom of the wall at a rate of 14 feet per second, at what rate is the top of the ladder moving down the wall when the top of the ladder is 7 feet from the ground? Okay, so this is a little right triangle, assuming your wall is not janky. And think about what's going to happen, right? If you were to take the foot, right, here I'll do it kind of like this. If you were to take this foot and then pull it away from the wall, what's going to happen with the top of the ladder, right? Obviously, it's going to go down, right? And we're going to assume that we're not going to like pull it all the way out. We're just going to assume that it like slides down really nicely. So as I take this foot and I pull it outwards, the top is going to correspondingly go down the wall, right? So that's what's happening. You're going to pull the foot away, which makes the top come down. So let's label those distances. I think it's nice. Just call this x, call this y. You can call this z if you want, but you really don't need to call it z because that's constant, and it tells me the ladder, right, that hypotenuse isn't going to change signs. Now, if you have something like this, that horizontal distance, it's not always the same. As you pull the ladder away, right, that horizontal distance gets bigger. And then this vertical distance, the y value, it doesn't stay the same. As you pull the ladder away, that's going to get smaller. But the actual length of the ladder, that never changes. So you don't need to call it z. You just straight up plug in the number. Right? It's 25. Who cares? So let's call this dx dt, and we'll call this dy dt. dt. Well, I'm kind of off the page. Sorry. So again, you're pulling the foot out, which is going to make the top come down. The ladder's 25. Let's figure out what else we got. The 25 is labeled. You're pulling the foot out at a rate of 14 feet per second. So there's your dx dt. It was 14 feet per second. That's what you're pulling it out. And keep in mind, like as you pull it out, the x value is getting bigger, so the dx dt should be positive. But then as you pull that x value away from the wall, and as you make that x value bigger, the y value should be getting smaller. So this answer should be negative, right? The dy dt should be negative since y is decreasing. But it says, what's the rate of the top of the ladder? So it wants me to answer, what's your dy dt at this instant when the top of the ladder is 7 feet from the ground? So at this one instant where the y value is 7. Okay, so that's good. Let's just start with our good old trusty Pythagorean theorem. Right, that's the theorem that you need anytime you have a right triangle and you're dealing with the side lengths of a right triangle. So x squared plus y squared equals 25 squared. That's always going to be true no matter what the x and what the y values are. No matter what moment of time, Pythagorean theorem still works. X squared plus y squared equals 25 squared. Okay. Now, let's take the derivative. So I'm going to have 2x dx dt, or x prime. If you like x prime, that's fine, plus 2y dy dt is going to be equal, it's not 225 then times d25. No, the derivative of 25 squared. Don't even bother to multiply this out. It doesn't matter. The derivative of that constant is 0. So it doesn't matter what 25 squared is. Right, but I start with Pythagorean theorem, take the derivative. Let's see everything that I know. 2 is 2. Ooh, do I know the x value? Well, not right away. I do know at this moment that I'm investigating, the height was 7, and this is 25. Could I potentially figure out what the x value is? Yes. All you have to do is Pythagorean theorem for that moment, right? X squared plus 49 is going to equal, I don't know what the 25 squared is. Anyways, you solve it, and the x ends up being 24, right? So just do 25 squared minus 49, then you square it. You can solve for the x value. It's 24. 7, 24, 25 is a Pythagorean triple. Right, so you kind of just know those integers, those whole numbers, they satisfy the Pythagorean theorem, and they work really well. Some other common Pythagorean theorems, 5, 12, 13, and then 3, 4, 5. You should definitely know that these are Pythagorean triples, and then any scalar multiples also work. Right, so 3, 4, 5 works, so 6, 8, 10 would also work, or 9, 12, 15, right, or 10, 24, 26, those would all work. All of these Pythagorean triples, or any scale multiple of them, will satisfy the Pythagorean theorem, and they work really nicely since they're all whole numbers. So since I knew that it was 25 and that one's 7, I kind of knew that one was going to be 24, but you could use Pythagorean to check. Anyways, let's get back into this. I found what the x value was. I wasn't handed it for free, but I could figure out that the x value at that moment is 24. It's not always 24, but at that one moment that I'm investigating, it's 24. And then the dx dt I knew was 14, positive, because the x value is getting bigger. 2 is 2. The y it told me was 7. dy dt is what I'm trying to solve for, equals 0. So here we go, right? We took the derivative, plugged in the stuff that I knew, solving for the one thing that I still need to know. So you just subtract this over. So we have, let's see, 2 times 7 times your dy dt, or your y prime, equals negative 2 times 24 times 14. You would divide it by that 2 and by the 7. Let's see, 2 times 7 is 14, so it's going to cancel. So it looks like your dy dt, 2 times 24 is 48. And then don't forget your units. You would need the units for y over units for t. So it'd be feet per second. Okay, so again, this is a perfectly fine answer. If it was a free response saying dy dt is negative 48 feet per second, that's fine. Since you're pulling that ladder away from the wall, the top of the ladder is going to be going down, right? So since y is decreasing, dy dt should be negative, right? That makes sense. But let's think about this. The question asks, how or at what rate is the top of the ladder moving down the wall? Well, if you said moving down at a rate of negative 48 feet per second, this is kind of like the tank one that we did in the last video. If you said moving down at a negative rate, that double negative would actually mean that ladder is going up the wall. If you're going down at a negative rate, then your ladder would actually be going up the wall. So you can either include the negative and just say, hey, dy dt is negative 48, or if you say moving down, you would only say it's moving down at 48, right? The moving down is the negative. So be careful. Sometimes it's going to want your answers to have the negative just with the word, or other times if it just says, hey, what's the rate of change of y? Well, saying the rate of change of y, that doesn't necessarily imply positive or negative, right? The rate of change of y is negative 48. But if you're saying, hey, how fast is y decreasing? Well, you wouldn't need to say decreasing by negative 48 feet per second. The decreasing already has the negative, so you could say it's just decreasing by 48 feet per second. So be careful. Either put the negative with the math or put the negative with the word, but don't put the negative word and put the negative with the number, right? Because then the double negatives end up kind of giving you the wrong answer. All right, negative 48 feet per second equals dy dt, that's fine, or it's moving down at 48 feet per second. Let's look at the next one. Try to finish all 5 of these in this video so I don't have to make a third one. I think we can do it. Well, I know we can do it. It's just how long I want this video to be. Anyways, third one. A fish is reeled in at a rate of 2 feet per second from a bridge that is 16 feet above the water. At what rate is the angle between the line and the water changing when there are 20 feet of line out? Okay, again, let's draw a picture. I like drawing pictures. Let's say we're going to assume that this fishing line is just cast from the 16. Like, we're not going to add on 6 feet for the height of the dude or whatever, or the female. We don't know who's fishing, but it just says gives us the 16. It doesn't say anything else, so we'll just assume that it's 16 total, all said and done. And then that fishing line is connected to your fish. I'm going to call that L for the fishing line. Let's call this X, and again, that's a right triangle. And if you had something to do, like if you wanted to know the dl dt or if you wanted to know the dx dt, like if you're only working with the side lengths, then yes, Pythagorean Theorem is what you'd want, right? Pythagorean Theorem, that's how you do right triangles with the side lengths. But really this wants the angle, and it wants the rate of change of the angle, not really the side length. So let's think. 16 obviously is constant. It's not going to change. The dx, as you reel in the fish, that x is going to be changing, and dx dt would be negative. And then as you reel in the fish, of course, the line is going to be getting shorter. So that's going to change. And then as you reel in the fish, right, think about it. This point on the top left is fixed. So as you reel in this fish, that angle is going to change, right? Or think about, I guess it would be the angle down here. As you reel in the fish, think about the angle. That angle should be getting bigger. But for certain, the angle is going to change. So that's a variable, that's a variable, that's a variable. So potentially those three rates to worry about. 16 is constant. It's not going to change. So that's good. Okay, let's figure out what numbers we can attach to which ones. Our fish is reeled in at a rate of 2 feet per second. So you're reeling in 2 feet of line every second. That's your dLdt, and your L is decreasing. So really you should say dLdt is -2. Okay, again, you could attach the negative in a different place later on, but I think it's easier to label it as -2. Okay, from a bridge at 16 feet above the water, that's great. At what rate is the angle between the line and the water changing when there are 20 feet of line out? So at this one instant, the L is going to be 20. I don't really know anything about the x or the dx dt. And then the d theta dt is what I want to know. Okay, so if we are looking for some type of an angle or the rate of an angle, I don't want to do Pythagorean theorem, because Pythagorean theorem is only about the side lengths. What I'd want to do is set up a SOHCAHTOA trig ratio. So remember from SOHCAHTOA, either from geometry or definitely from pre-cal, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So I want to figure out, hey, which two side lengths of this triangle do I want to use, and then set up a trig ratio based on that angle theta using those respective sides. Now let's think about the options, right? We have the 16, we have the x, and we have the L. Which two sides do I want to use, and then which side do I really not want to use? Well, the one that you don't want to use should be obvious. I don't know the x value. Could I find it? Yes. Will we find it? Yeah, we will later because we're going to have to. But initially, I don't know anything about the x or about the dx dt. So since that's the side length that I know the least about, I probably want to avoid using it. Like, let's set up a trig ratio that's going to use the 16. Yeah, certainly you'd want to use the constant. And then we would also want to use the L, because I know stuff about the L and about the dLdt. So let's see. I want to use the opposite and the hypotenuse. So I'm thinking here a sine ratio is going to be the best way to get this answer. So let's set it up. Sine of theta is going to equal 16 over L. Okay, now we're actually ready to take the derivative right now. Let's do it. Sine of theta, when you take the derivative, you'd have cosine theta times d theta dt, or if you want theta prime, the derivative sign is cosine, then you have your d theta dt. This is a power rule, right? I'm going to do it over here. That would be 16L to the negative first power. So that -1 would multiply to the front and then decrease. So this ends up being negative 16 over L squared, and then times your dl dt. So we actually took the derivative with respect to time. And now let's try to plug in everything that we can. Okay. The d theta dt, that's what we're trying to solve for. So, of course, that's still going to be missing. Let's look on the other side. Negative 16, I can plug that in. The L squared, I can plug that in. That's 20 squared. And then the dl dt, since it's multiplied, I'm going to put that dl dt on the top. So the dl dt was -2. Now, that one's plugged in, that one's plugged in, that one's still just copied over. I need to figure out what the heck is cosine theta. And you're like, okay, Mr. Bell, well, I don't know the angle, so how do I get the cosine of the angle if I don't know the angle? Well, you don't need to know the angle, right? The cosine is just a ratio. The cosine of any angle is always the ratio of the adjacent side over the hypotenuse. And I know the hypotenuse is 20, right? So cosine is adjacent over hypotenuse. I know the hypotenuse is 20. So if I could only figure out what that darn x value is, well, then I could figure out as a whole what that cosine value needs to be. So let's go think about it. We know that's 16, that's x, that's 20 at this one instant that we're investigating, right? Here's your angle theta. Could you use Pythagorean theorem to solve for x? Yes, it's actually going to be a Pythagorean triple, right? It's your 3, 4, 5. Divide that by 5, you get 4, so divide that by 4. So I think this is going to need to be 12, right? So you could figure out what the x value was, and we needed to. Actually, there would be a way to do it without, but this is the easiest way. So your cosine of theta, without ever knowing what the angle is, you can still do the cosine of theta. Once you find the adjacent side and you know the hypotenuse side, you just put the adjacent over the hypotenuse. then you're going to be good to go. Okay, now let's solve it. We want the d theta by dt by itself, so I'm going to multiply the 20 over. So I have negative 16, negative 2, multiply the 20 over, and then divide by the 12. Okay, so let's try to simplify it. The 20 will cancel, right? That's going to cancel with that 20. Let's see if we could reduce it. Let's see. This will divide by 2, so that's gone. Obviously, the 2 negatives are going to go away. So right now I've got a 16. And then I've got a 10 times a 12. You can still do a little bit more reducing. Like how about let's reduce this by 4. And then this by 4. And then I think that's it, right? I don't see anything else. That's actually, nope, that's going to reduce by 2. That's going to reduce by 2. So it looks like I have a 2 on the top and then a 15 on the bottom. Okay, so it looks like your d theta dt. Of course, if you have a calculator, you can use the calculator. I don't care. But the point is, you really should be able to do this stuff without a calculator. Just look for little things that reduce, right? Use your middle school math. You don't have to multiply out the whole top and then divide it by the whole bottom. That's really making the problem a lot harder than it needs to be. Just look for things that individually reduce and then just make your life simple. But d theta dt ends up being 2/15, and then your units would be radians per, I think it was second, right? Second. The units for your degrees, or the units for your angles, are always going to be in radians, unless it tells you otherwise. If it says something about degrees, then you could use degrees. But 2/15 of a degree a second, that would be a very, very, very small change, right? 2/15 of a degree. That's like, I can't even make my fingers that narrow, right? 1 degree, what, 2, like, no, it's too small. 2/15 of a radiant is at least more significant, right? But the units for an angle is always radians, unless it specifically tells you degrees. And let's think, does it make sense that it's positive? Well, as that fish is reeled in, it does look like, right? Remember, you're kind of dealing with this angle here. And as that fish is reeled in, right, that line is getting steeper and steeper and steeper. So yes, the angle should be increasing. So yes, it should be a positive result. It's always good to make sure we're kind of getting the right sign at the end. So whenever you have a right triangle, there's really two options: Pythagorean theorem or a trig ratio. If you have to do something with an angle, you need to do a SOHCAHTOA. You need to do one of those trig ratios. If you're only working with side lengths, then all you need is Pythagorean theorem. Right, so right triangles are pretty common. Pythagorean or SOHCAHTOA, those should always be pretty doable. Okay, 2 more, I think. I'm getting tired. You're like, I know, you're telling me, Mr. Bell. I'm getting tired just watching you. Wish you would stop talking. That's right, 2 more examples, then I'll stop talking. A man, ooh, this one's like my least favorite one too. Oh my gosh, why do I put it at the end? It says, a man who is 6 feet tall walks at a rate of 5 feet per second towards a light pole, and that light pole is 16 feet tall. We already got this diagram, it's measured. It's labeled for us, that's really nice. Part A, at what rate is the tip of his shadow moving when he's 10 feet from the base of the light? And then part B, at what rate is the length of his shadow moving when he's 10 feet from the base of light? These shadow ones are weird. They don't typically come up on the AP exam. They could. It's technically in the curriculum, so it could. But they usually don't come up, right? But here's what I would suggest. If you see questions like this, figure out a way to set it up the same way every single time, right? Just whatever you do, just do it consistently. And what I like to do is like this, right? Obviously, you have this light pole. It's going to hit the guy's head, which creates this shadow, right? And I'm going to call the shadow S, right? So the length of the shadow for me is S. And then I'm going to call this distance right here X. The distance from the man to the light pole, I like to call that distance X. And then this total distance from the light pole to the tip of the shadow, I call that Y. So again, S is the length of the shadow, and then Y is the distance to the tip of the shadow. And then X is the distance between the guy and the light poles. And if you always set it up with X's and S's and Y's, if you always set it up the same way, then there's going to be some consistency with how you could always solve them the same way. You don't have to use X, S and a Y, you could use whatever variables that make you feel warm and fuzzy, right? Because they're variable. You could literally use smiley face, lightning bolt, and stars if you want. I don't care. Just whatever you do, do it consistently, because that's going to help you remember in the future, right? I always do X, S for the shadow, and then Y for the total length. Okay, so let's think about this. The key, let's label what we have. 6 is already there. He's walking 5 feet per second. And obviously, as this guy walks, the x value is going to be changing. So dx dt, and then as he walks, the shadow is going to be changing. So ds dt, and then of course as he walks, right, the dy dt. Y is also going to be changing. So they're all variables, right? The only thing that doesn't change is the height of the pole and the height of the guy. But all those other things change. And it says the dx dt, he's walking at this value. The dx dt is -5. Since x is decreasing, he's walking towards the light post, right? That x value is getting smaller. The dx dt is a -5. Okay, now part A, let's read it. It says at what rate, so it's asking for a derivative, but it says at what rate is the tip of the shadow moving when he's 10 feet. So at this one instant when the x is 10, what's that rate of the tip of the shadow going to be changing at? Remember, the tip of the shadow was y. So part A, it's really looking for dy dt. Right? Part A, it wants dy dt. Part B says at what rate is the length of the shadow changing. So part B is it wants you to find ds dt. Okay, so we're going to find everything, right? The s and the ds dt, or actually we're not going to need the s or the y. We're just going to get the ds dt and then the dy dt. Okay, but kind of like with the tank ones, this boils down to some similar figures, right? And specifically, we have some similar triangles in this diagram. Let's try to find them. Similar triangles, right? I have this big triangle, and then I have this little triangle, and they both share the same vertex, right? So again, you have the big triangle, and then you have this smaller triangle. Those are similar figures, so they would be proportional to each other, right? There's the big triangle, which is 16y, and then I don't know what that diagonal is. That's not labeled. And then we have the smaller triangle, which is 6, and then s. And those are going to be proportional to each other. So let's set up a ratio. 16 over y equals 6 over s. You don't have to do it like that. You could do 16 over 6 and then y over s, or you could do 16 over or 6 over 16. There's all sorts of different things. Just do it consistently and you'll be okay. Cross multiply. Don't plug in anything, right? Because those are both variables. They're going to change. But cross multiply, and you're going to end up with 16s is equal to 6y. Let's reduce it. It divides by 2, so I get 8s is equal to 3y. Okay, so you're like, that doesn't really help, Mr. Bell. Well, it will. Let's try to think about what I want, right? Because right now I've got this equation, 8s equals 3y. If I took the derivative right now, I would have 8 ds dt equals 3 dy dt. And then I would get stuck because I don't know either of those two. Right? It doesn't really matter which one we find first, but when I am looking for the first one, I'm going to somehow have to bring in x's, because I know what the x is. It's 10, and I know what the dx dt is. It's -5. So I can't start off with s's and y's, because if your original has s's and y's, then your derivative will have s primes and it'll have y primes. And we're missing both of those. So let's try to do something really quickly. I'm going to erase that. I'm going to come back to it in a little bit. I'm going to erase it for now. Remember, I don't want s's and y's. I need to somehow get rid of them and then get it to being in terms of x's and something. Let's do part A first, right? So if I want to solve for dy dt, I would need to keep the y and then get rid of the s. Right? Because if I get rid of the s, then I'm not going to have a ds dt. I want to keep the y, so that way when I take the derivative, I still have the dy dt. So I need to somehow get rid of this s value. And the variables I'm okay with having are, of course, y's and then x's. So let's go think about some geometry. This piece is x. This piece is s. And then this total, right? The total is y. Let's think about how could I write an expression for s in terms of x and y. Well, think about it. If I had the total and I subtracted x, wouldn't that give you s? Segment addition. I know x plus s equals y, therefore s is y minus x, right? So then I could plug that in, and then I could distribute, and then just add that stuff over. 5y equals 8x. Okay, so I couldn't take the derivative here because I would have been stuck. I didn't know s prime or the y prime, so I would have been stuck. So you need to figure out which one do you want first. And if you want the y's, you can't get rid of the y's. You'd have to get rid of the s's. You're okay with y's, you're okay with x's. And then here we simplified it. And now I still need to take the derivative. But now I think I am ready to take the derivative. Here I'd have 5 dy dt, or y prime, equals 8 dx dt. Again, if you like s prime, y prime, and x prime, that's fine. Use the primes. Or if you want to use the t's, that's fine. But here I had to switch it to x's because I'm okay having the dx dt because I know what that value is. Let's plug it in 5, and then dy dt is what I'm trying to solve for. The dx dt I knew from this question was -5. Look, the 5s are going to even cancel, so I get that dy dt is -8, and then I need the units for y over the units for time. So feet per second. Okay, so we had to get the first one, and the first one is always a little bit tricky. Once you have the first one, the second one's a little bit easier. Here's what you could do, right? Come back to this original equation, right, which is from the similar figures from that proportion. Now that I know dy dt, like I don't have to, if I want to solve for the s, I don't have to get rid of the y's. I could take the derivative. And previously, this was a problem because I was missing both of those. But now I know what that one is. I can plug it in. ds dt equals 3. I don't know why I put parentheses around that. But the dy dt, now I can plug it in as -8. And look, the 8s are going to cancel, and I could get that ds dt is going to be -3 feet per second. Okay, so we were looking for the ds dt and for the dy dt. That was B, this was A. You started off with this equation with s and y, and if you take the derivative, like you could do the derivative, but you would get stuck initially. The first one that you solve for, you need to bring in x's. But once you have that first value, the second one's a little bit quicker. I'm going to do it one more way, just for extra fun, right? I'm going to do it down here. Now let's say if I had wanted to do the part B first, so I have 8s equals 3y. If I wanted to get the ds dt first, I could, all right? But I would need to get rid of the y's in order to do so. Once you know the y's, you can plug it in. But if you wanted to get rid of the y's, you could have. So let's think about it. What would y be equal to? Well, we already know. It's x plus s. So here I'd have 8s equals 3x plus 3s. Bring that over. 5s is equal to 3x. So I could have done, right, just like what I did to get the first answer on A, I could have done a similar thing to get the answer to B. And then that would have been 5s prime equals 3x prime. And then plug in the x prime was -5. Look, the 5s are going to cancel, so you'd get your s prime as -3 again, which matches. But you don't have to go through and do all this work, right? You don't have to avoid the y's. Once you've done part A and you know the y prime, that second part is a little bit faster. But the first one you want, right? Whether you want the y prime first or whether you want the s prime first, the first thing that you solve for, you have to use x, because x is the only thing that you initially know about. But once you fuse that x to find that first other rate, either the y prime or the s prime, once you have that second rate, then finding the remaining one is pretty easy. You could do the same process, but you don't have to switch it to x, because once you know the y is no longer a problem. You could do it, and you should get the same thing if you do it, but it's not necessary. Whew, okay. One more, and then we're done. Oh my gosh, I'm sorry. These are hugely long videos. I know, it's not fun. I'm getting pretty tired too. But it's all right. One more, and then we're done. A trough is 10 feet long and 6 feet across the top. I always think that's a weird word. Trough. It looks like trogue. I don't know why it's pronounced with a TH at the end. I'm going to call it a trogue. A trogue is 10 feet long and 6 feet across the top. Its ends are isosceles triangles with an altitude of 4 feet. If water is being pumped into the trogue at 9 cubic feet per second, how fast is the water level rising? When the water is 2 feet deep. Okay, this is another tank container one with liquid inside of it. These are common. This one's going to boil down to some similar figures and some proportions. Let's go ahead. I'm not going to use the pen because it's going to make things hard to see. We've got this dimension, which is 10, that dimension, which is 6, and I've got this height, which is 4. I'm going to say height is 4. And then let's see, we have this prism of water inside. So I have this triangular prism, of course, for the container itself, and then I'd also have the triangular prism of water within the container. Now this would have a height, and then that, I'm going to call it B for the base. Let's call this the capital B. Capital B was 6, right? That's the total width across the top, and then this little b. Oh, wow, that diagram's terrible. Let me show you this really quick, just because that's like, I don't know how I drew it so much nicer on my other notes key. But here you have this rectangular or this triangular prism of water in the tank. It's got a little base, and then it's got a little height, and then there's your big base, and then your big height was 4. Okay, that's great. My diagram, I guess I'm just really tired. My diagram is very ugly. Oh well. But the trick is still going to be similar figures. So let's set up some proportions. Similar figures. Again, this big one is going to be proportional to the little one. And I like to do big over big. It's going to be proportional to little over little. Don't plug those in, right? The things that change, the things that are variable, do not plug in until after you take the derivative. But these capital ones do not change, so you can plug them in. That was 6, this was 4, so it looks like I've got 3 over 2 is b over h, cross multiply, 3h equals 2b, and now I've got some way that these two variables are connected together. So if I had to solve for h, it would be 2b over 3, or if I had to solve for b, it would be 3h over 2, right? So if I had to make a substitution, I could change the h into 2/3 b, or I could change the b's into 3/2 h, right? If I had to get rid of one and turn it into the other, I would be able to do so. And it really doesn't matter which one I know and which one I need to get rid of. You could do either way. And the trick is similar figures. So anytime you have a container with stuff inside of the container, similar figures, setting up a proportion, setting up these ratios, that's the trick. Okay, let's think what this question gives me. It says a trogue is 10 feet across the top. That's here we go. That's kind of like the width, so that's good. 6 feet across the top. That's your big B. Height of 4, so that's good. Water's being pumped into the trogue, so we've got an inflow. That's your dV dt. Again, pay attention to the units. It says 9 feet cubed per second. So it's units for volume over time. So that's your dV dt. And if you're pumping water in, the volume is increasing. So the dV dt should be a positive 9. Then it says how fast is the water level rising when the water's 2 feet deep. H is a variable, so potentially we'd have a dH dt involved, and that's what it wants. B is also a variable. But we really don't need to know the dB dt, right? We could find it, but that's just creating extra work for yourself, right? We want the dH dt, that's the water level, and then specifically we want the dH dt when the water is 2 feet deep. Okay, but again, it starts me with the rate of change of the volume, so I probably need a volume equation and then going to take the derivative of it. So let's think about it. I've got my dV dt, I've got my h, got my capital H, got my capital B. I don't know really anything about the lowercase b's, so hopefully those will go away. And then the dH dt is what I want. Let's think about it. The volume of this container. The volume for anything is always area of the base and then times the height. Right? Really, the height is really more like a width here, right? So I need the area of the base. Really, we're doing the volume of the water. So I need the area of the base times the height. The height is going to be 10. All right, so here we go. The volume of the water is going to be 1/2. The area of this base, it's going to be 1/2 B times H times 10. That's really your height of your prism. So the volume of water, you need the area of the base, so B times H, and then times 10, and then 1/2, obviously. All right, let's simplify it. So the volume is going to be 5BH. Again, like, if you knew everything about all the variables, you could take the derivative right now. You'd have V prime, you'd have 5, and then you could do product rule. Derivative of the first times the second plus the derivative of the second times the first. If I knew everything about both of the variables, then yeah, you could just take the derivative product rule and plug in everything. But I don't know this, I also don't know this, I do know this, and I don't know that. If you tried to take the derivative right now, you would be stuck because there'd be too many unknowns. There'd be too many missing pieces. We only want one missing piece. So since I don't know anything about the b's or the b primes, I need to get rid of them. So let's go back over to the substitution, and then here's the one that I'm going to use. I need to get rid of the b's because that was the variable I really didn't know anything about. So let's make the substitution. We got 5, and then instead of the b, plug in 3h over 2 h. So then this volume looks like it's 15 over 2 h squared. So now I've got the volume equation based only on the variable h. So think about it. Am I ready to do calculus? Hopefully. If I have v's in my original, when I take the derivative, I'm going to have v primes, dv dt's. And if I have h's in my original, that means I'm going to have h primes. Now, it's okay to have h primes because that's what we're trying to solve for. And it's also okay to have v primes because I know what that value is. I didn't want b's because that was too many extra missing things. But now we are ready to do my calculus, which is to take the derivative. So we got dv dt, and then let's see, that 2 is going to multiply to the front, cancel, so I have 15h times dh dt. You can either write the dv dt or the dh dt, or you could put the primes. It's equivalent notations. Just remember, if you're doing h prime, that's dh over dt. You have to kind of mentally keep track of what variables are where. Okay, so the volume we knew was 9, or the volume rate was 9, 15 is 15. At this moment, the height was 2, and then your h prime, so here we go, 9 divided by 30 equals your h prime. That's going to reduce to 3/10. And then let's see, units, so that's dh dt, so I need the units for the height, which was feet, and then the units for the time, which was second. And let's think, does it make sense? If water is flowing in, should the rate be positive? Well, yes, if water is flowing in, the height's getting bigger, the water level would be rising, so yes, the h prime should be positive. The water level would be rising at 3/10 feet per second at that specific moment of time. Remember, do not plug in the h value until after you take the derivative. If you plug in the h value here, right, you'd have v equals 15 over 2, and then you'd have a 4. If you plug in this number before you take the derivative, your v prime would be 0, and that logically doesn't make sense. V prime can't be 0 when you know it has to be 9, right? So make sure you take the derivative first before you plug in those instantaneous momentary values. All right, that's the end of all the related rates videos. I know it's hard. I know the homework is going to take a while. I would really advise not to procrastinate. Try to do it like a couple days at a time. Try to do it chunk by chunk. If you wait and do it all at once, it's going to take a while, right? This is not easy. It's supposed to be hard. It's one of the 2 hardest things we do all year, and I'm sorry to break it to you, but it's not hard because of the calculus. Because out of all this, one step is calculus. And that step isn't too bad. That's just taking a derivative. It's all the non-calculus stuff that makes these related rates questions hard. And the only way to get better is just to practice. So please do the homework. It's important that you do it. Please check your answer keys with what I have, or please check your answers with the answers I have on my answer keys. And then make sure if you have any questions, you bring those to me so I can help you out, because this is definitely not super easy.